Okay. Now, see, basically image location is the common point from which the reflected rays pass. Now we have drawn some reflected rays here. I'll call them as R1, R2 and R3. After reflection, they are not coming towards each other. They are going away from each other. They are diverging after reflection. So what we do is we extend them in the backward direction such that they seem to be coming from a common point. That's the image position that we have identified here. Okay. Suppose, okay, forget the observer, or okay, let me just copy this diagram. Maybe just the mirror. Let's say this is the mirror, object is in front of it. You know, image will form exactly behind the mirror at the same distance. Okay. What if the mirror only extended from there to there? Okay, suppose this is the mirror. Will an image still be formed? If yes, where will it form?
Top right corner.
Top right corner. So Rishi, you are saying the image will form here.
Yeah, yeah, sir.
We'll see. We'll see. Can you justify why do you think the image forms there? Or see, basically, image has formed there means it should appear as if rays are getting reflected from that point, or rays are originating from that point. How will the rays appear to originate from there? Others, Anugraha, Shashank, do you think an image will still be formed? If yes, where?
So the image will be formed like directly behind the mirror at the same point. And to represent it, you have to extend the mirror like
Okay.
with a dotted line.
Okay. So you are saying image will be formed somewhere here, like as it was formed before. Okay. Anugraha, what do you say?
Sir, I also think it will be formed there, the below point.
Okay. Second case. Fine. Fine. See, it all depends on how the rays get reflected. Now, the mirror is not like if you cannot draw a perpendicular line from the object onto this mirror. So what? If any light falls on the mirror, it reflects the light. So you can imagine a few rays. Now see, this is a point object. Point object reflects or emits light in all directions that we had discussed in the last class. Now imagine some rays from the object onto the mirror. Some of the rays coming from the object will definitely travel this way. Okay, so let's say this is one of them and assume this is another one. Just a moment. You can take a ray like this. Now, according to the laws of reflection, angle of incidence should be equal to angle of reflection. So the first ray maybe gets reflected like this. And the other one, again, angle of incidence should be equal to angle of reflection. So if I maintain that, it gets reflected somewhat like this. And in between these two rays, there will be infinite other rays also striking the mirror and getting reflected. For example, you can take one more like this. You should always visualize rays from the object falling on the mirror or lens or whatever it is and getting reflected or refracted. Only then your answers in optics will be correct. Okay. So if we now imagine an observer somewhere here, observer could be anywhere in front of the mirror. Rays entering the observer's eye, okay, these reflected rays, R1, R2, R3, in between them also there are infinite other rays. Some rays will definitely enter into the observer's eye. Where will those rays appear to be coming from? Okay, those rays, if you extend them in the backward direction, they will all appear to be coming from this common point. Rishi, do you agree with this or not?
Yes, sir.
Huh. So this is where the image forms. Okay, this is not correct. This is correct. So whether it's a complete mirror or a broken mirror or only a part of a mirror, the image will form as if it was a complete mirror. Okay, because had the mirror extended all the way till here, the image would have formed here. Basically, where the image forms depends on how the rays get reflected. And the way the rays are reflected is the same whether it's a complete mirror or only a partial mirror like this. Okay, but there will be one difference between the image formed by a complete mirror and a partial mirror. One small difference will be there. Basically, it's the brightness of the image. Because bigger the mirror, greater the number of rays that are reflected. Okay, and when more light enters into our eye, we see the object brighter. Object or image appears brighter to us. So in terms of brightness, there may be a difference, but the position of image is the same, whether it's a complete mirror or only a part of the mirror. Okay, image will form where it would have formed had it been a full mirror. Okay. Fine. We'll discuss some more cases of plane mirror later. First, let us derive the mirror formula. Let's assume there is a curved mirror. Now, mirror, is a surface actually. It's not a curve. It's a surface. It's either a flat surface or a curved surface, like a spoon. The concave side of the spoon, convex side of the spoon, or mirrors itself you may have seen, no? Concave mirrors, convex mirrors, plane mirrors. Okay, so it's a surface. And curved mirrors are basically curved surfaces, shiny curved surfaces. They are what you call as curved mirrors. And any curved surface can be assumed to be part of a sphere surface. So assume there's something like this. Just a moment. Consider a sphere. Okay, in 2D it looks like a circle, but this is actually a sphere. Assume its radius of curvature or radius of the sphere is r. Radius is the distance from any point of the sphere to its center, you know that. Let's mark the center as C. And for now, let's just call this point as P. So the distance from C to P or P to C is equal to R. Okay. Now, assume this sphere is coated on the inside. Okay, coated means silver coated on the inside. So inside is shiny, outside is rough. So basically, this is the shiny side. This is the dull side. And the shiny side becomes the reflecting side. And in this case, the shiny side is concave. So this becomes a concave mirror. Like the inner side of a spoon. Right? So any curved mirror can be assumed to be part of a sphere like this. They won't show you the whole sphere. You can consider that curved surface to be part of a sphere. That sphere's radius itself is called the radius of curvature of this mirror. Yeah, that is R. Okay. Let me remove all these. Okay. Now what we are interested in is finding out what kind of images this mirror forms. Okay, if we put an object in front of it, where it forms the image, what will that image look like compared to the object? All those things. That is what we are interested in. So first thing we will derive is the relation between object distance and the image distance. relation between object distance and image distance for a mirror is what we call as the mirror formula. Okay, so it's clear that this is a concave mirror. Let it be. Let's just extend this line. Okay. Now, some of you may be quite comfortable with all this, but it's important to know how the formula is derived also. Suppose there's an object somewhere here. We are considering a point object as of now. Let this orange dot be the object. Now, from that object, many rays will strike the mirror and they'll get reflected following the laws of reflection. Okay. You can imagine one ray from the object traveling straight like this along this line that we have indicated. Okay. Now this ray strikes the mirror perpendicular to it, means it strikes the mirror along the normal. Can one of you tell me what is the angle of incidence of this ray?
0, sir.
0. It is striking along the normal, so angle of incidence is 0. Therefore, angle of reflection will also be 0. It will be reflected straight back along the same line. Okay, that's one of the reflected rays. Let it be. Consider one more incident ray, maybe from here to here. Now we have to draw its reflected ray. For that, we should first visualize the normal. Listen, why these derivations are important is because they teach you how to draw the ray diagrams. Okay, we took an incident ray. Now we have to draw the reflected ray. Why? Because we want to locate the image. We want to find out where the image will form. And image in this case is nothing but the common point through which the reflected rays pass. Incident rays are coming from the object. Reflected rays will come from the image. So we want to find out the common point through which the reflected rays pass. Okay. For that, we have to imagine the normal. Can one of you tell me how to draw a normal to a spherical surface?
The line joining the point of incidence to the center of the.
You just connect the center of the sphere to any point on its surface, automatically it becomes a normal. So let's say this is the second incident ray. Now call the point of incidence as A. That's where the ray strikes the mirror. Just join A and the center of the mirror, that center of curvature of the mirror, that becomes the normal. I am drawing it in dotted line. This is the normal. And why do we need to draw the normal? Because that will help us draw the reflected ray. Keeping the angle of incidence is equal to angle of reflection. I can easily draw the reflected ray like this now. This way. Fine. So one incident ray was taken along the line OCP. It gets reflected straight back. Another incident ray from O to A, it gets reflected this way. In between these two, or on the lower side of the mirror also, you can draw any number of incident rays you want. You will get a lot of reflected rays also. Okay, infinite incident rays and infinite reflected rays will be there. But if two reflected rays meet somewhere, the other reflected rays also will meet at the same point itself. Okay, suppose this is another incident ray. The reflected ray from there will also pass through this point. Okay, so you can take any number of incident rays as you want. You can take some on the lower side also, lower side of the mirror. Maybe one like this gets reflected this way. So they all pass through a common point, and that point is what we call as the image location I. Why is that the image location? Because if there's an observer in front of this mirror, anywhere, the observer could be on the lower side or the upper side, whatever, light enters into the observer's eyes as if it is coming from that point. So when we look towards the mirror, we will see something here. That's why we call it the image location. Okay. Now we have to do some calculation and derive a relation between object distance and image distance. So we'll will take only 2 rays because other rays anyway pass through that point, but there's a condition. I'll tell you the condition also. Fine. Now here OA is a straight line, OP is a straight line, but A to P is a curve. Okay, clearly it's a curve. But if you take the incident ray very close to the point P, meaning I'll draw one incident ray in yellow color. Take it like this. If you take an incident ray this way, the reflected ray will pass through that point, the location of the image. It will pass like this, but then AP will almost become a straight line. And that straight line will be perpendicular to OP. Okay, so AP perpendicular to OP. When does this happen? When incident ray makes a very small angle with OP. Okay, then AP will almost be a straight line and it will be perpendicular to OP. We are going to consider that assumption. Okay, so whatever we are deriving after this will be valid only when the incident rays are parallel, not parallel, incident rays are very close to that line OP. Okay, there is a name for them. We'll discuss all that. Fine. So assume AP is a straight line and that straight line is perpendicular to OP. Now what do we want? We want a relation between object distance and image distance. Let's say object here from the point P, okay, we take all distances from the mirror. So let's say the object here is at some distance U. Object distance is usually denoted by the symbol U. And image here is at a distance V. And from center to P, from center of the sphere to P, you know that distance is called the radius. So C to P is the radius. Let it be like this. Okay. Assume this angle is alpha, this angle is beta, this angle is gamma. Now here you can see the angle of incidence I, and on this side is the angle of reflection R, which are equal. I is equal to R. Laws of reflection. Fine. Now from basic properties of triangles, okay, you all must be aware that external angle is equal to sum of internal opposite angles. Consider the triangle OAC. Beta is an external angle for it, and the internal opposite angles are alpha and I. So can one of you tell me the relation between alpha, beta, and I? Relation between alpha, beta, and I. Fine. So tell me, in the triangle OAC, how are the angles alpha, I, and beta related?
Alpha plus I is equal to beta.
Okay, beta is equal to alpha plus I. One equation. Next, the other triangle, the smaller one, CAI. Center, that point of incidence, and the image location. How are beta, R, and gamma related? Rishi, can you tell? Isha, can you answer? How are beta, R, and gamma related? Okay, fine. For that triangle, gamma is an exterior angle. exterior or external, whatever you call, it is equal to the sum of internal opposite angles. So gamma should be equal to beta plus r, the angle of reflection. And we know angle of reflection is equal to angle of incidence. From the first equation, I becomes beta minus alpha. Okay. From the first equation, I is equal to beta minus alpha. I is same as r. So we'll put beta minus alpha here. Send alpha this side. Therefore, alpha plus gamma is equal to 2 beta. Okay, that's the relation between the angles that you see in the diagram. We still have not made use of the property that AP is perpendicular to OP. Okay, we still didn't assume A is very close to P. So generally from properties of triangles, this is valid. Alpha plus gamma is 2 beta. Okay. Now, if A is very close to P, okay, then AP becomes a straight line. Visualize it as a straight line here, somewhat like this. Okay, very vague, but fine. Imagine AP is a straight line. Then you know AP will be perpendicular to OP if A is very close. Then what happens? The diagram changes to this. Just a moment. Okay, not necessary. In this itself, you can tell. Imagine AP perpendicular to OP. So this is now effectively a right angle triangle, OAP. Okay. Similarly, the other two triangles also become right angle triangles. CAP is one right angle triangle, and IAP is another right angle triangle. So 3 right angle triangles will be formed if A is very close to P. Now tell me, in the triangle OAP, the biggest right angle triangle that you can see, what is tan alpha equal to? What is the side opposite to alpha?
AP.
AP, and the adjacent side is OP. So tan alpha AP divided by OP, and when A is very close to P, this angle alpha is a small angle. And for very small angles, tan alpha is equal to alpha itself. It's a mathematical approximation. So this is approximately equal to the angle alpha. Okay. So whatever steps we are taking from now onwards are all valid when this assumption is valid. A is very close to P. So this has a condition. Next, tan beta. Beta belongs to the triangle CAP, and tan beta is opposite side AP divided by adjacent side CP. So AP divided by CP, and beta will also be a small angle. So this is approximately equal to the angle beta itself. And similarly, tan gamma belongs to the angle triangle IAP, and tan gamma opposite is AP divided by adjacent is IP. And small angle, so approximately equal to gamma itself. This is how we relate distances to angles. And remember, this relation is valid only under that approximation or assumption. Okay. Now we will plug in these values in this equation. Alpha plus gamma is 2 beta, that we derived from properties of triangles. So from this we can say, since alpha plus gamma is 2 beta, what is alpha? AP by OP. Plus what is gamma? AP by IP is equal to 2 times of beta is AP by CP. AP cancels. That's all. OP is the distance of object from the mirror, U. CP is the radius. IP is the distance of image from the mirror, that is V. Therefore, we get 1 by object distance is U plus 1 by image distance is V is equal to 2 divided by center distance is the radius. That's all. This is the relation between object distance, image distance, and radius of curvature in this case. Right? But we derived this result in a particular case. What particular case? What's the kind of mirror we took? Concave mirror. Where did we keep the object? We kept the object beyond the center. Okay, so if you change the object position, or maybe you change the type of mirror, the formula could change. Sometimes you may get negative answers also. Okay, so we need a formula which works in all cases. This formula that we have derived, the standard derivation that you'll find in NCERT textbook also, is valid in this particular case. Okay, so what we'll do is we'll follow some rules which make this same formula applicable in all cases. Okay, those are called the rules of sign convention. Basically, these rules tell you how to substitute object distance, image distance, and radius such that this formula works in all cases. Okay. First rule. Can you all tell me from where should all the distances be measured?
The pole.
All distances must be measured or considered from the pole of the mirror. How do you get this pole point? Which point of the mirror should be taken as the pole? It's the point where the line connecting object and center meets the mirror. Like in this case, this point P itself is the pole. From object, you connect the center and extend it onto the mirror. That point is what you call as pole. Okay. And that line connecting object, center, pole, and extended beyond, it's called the principal axis. There's no rule that this should always be horizontal. For example, if you consider a situation like this. Just a moment. Center is center itself, center of curvature. You can't change that. I'll have to erase all this. The principal axis and pole are what we are trying to find out. Suppose the object is somewhere here. Then, one second, is my voice clear? Microphone is showing some error.
Yes.
Clear? Okay. Now, if the object is like this, then this line becomes the principal axis and this point becomes the pole of the mirror. It's not necessary that principal axis always be horizontal. Okay. Line connecting the object center and extended onto the mirror is what you call as principal axis. Where that line meets the mirror is what you call as pole of the mirror. Okay. Fine. So all distances must be measured from the pole of the mirror. So pole is like the origin for us. Next. Now usually we take one side of the origin positive, the other side of the origin negative. In mathematics, we call right side of the origin positive, left side negative. But in optics, it's not like that. Can any of you tell me which side of the origin should be taken positive?
The direction of incident ray is considered positive and the direction opposite is negative.
Correct. You have to see which way, you have to imagine which way the incident rays are traveling. The direction towards which the incident rays are traveling is considered positive. And automatically the opposite direction is considered negative. Like in this case, okay, in using which we have derived the formula relation between object distance images, incident rays are going to the right. Therefore, the right side part of the principal axis will be considered positive and the left part of the principal axis will be considered negative. Anything on the right of the pole is a positive distance. Any distance on the left of the pole is a negative distance. Pole is the origin, no? So which side to take positive is determined by the direction in which the incident rays are traveling. Here object was on the left side, so rays are going to the right side, therefore right side is positive. If object is on the right side, rays will come to the left side, then left side will be taken positive. So you have to visualize rays traveling. Okay. Fine. So along the principal axis, which side to take positive, which side to take negative is given by this. It depends on the direction in which incident rays are traveling. Then in the direction perpendicular to the principal axis, okay, anything above the principal axis is taken positive, below is taken negative. So in a direction perpendicular to principal axis, distances above the principal axis are considered positive and below it are considered negative. If you follow these three rules and substitute distances, then this same formula 1 by v plus 1 by u is equal to 2 by r becomes applicable to any kind of mirror, any kind of object. Okay, but remember this formula is valid under this assumption A is very close to P. Okay, now if A is very close to P, it means all the incident rays are very close to the principal axis. Okay, such rays are called paraxial rays. Rays close to the axis, they are called paraxial. Okay, and this approximation is called paraxial approximation. Okay, so whatever formulas we are going to use in optics are all valid only under the assumption of this. Okay, fine. So let's solve some problems based on this. Let's start with this case itself. But I'm telling you again, never solve problems in optics without imagining the rays. If you visualize the incident ray, reflected ray and all, then the answer will make more sense. Okay, just a moment. Suppose there's an object like this in front of a concave mirror. Okay, paraxial approximation and all are valid. You don't have to bother about that. Assume the radius of curvature is 20 centimeters. Now see, in problem, they'll always give you the radius positive only. For a surface, radius is positive only. When you use the rules for sign convention and substitute, then sometimes radius will be positive, sometimes it will be negative. You need to be careful there. Object is beyond the center clearly. Let's say it is at a distance of 30 centimeters from the mirror. Find out where the image forms. Okay. What is the mirror formula? 1 by V plus 1 by U is equal to 2 divided by R. Radius is given to you, object distance is given to you. Just substitute it carefully along with sign convention. You will get the image distance. Okay. Isha, can you unmute?
Yes, sir.
Any answer?
I'm doing, sir.
Okay. Tell me, you need to calculate image distance, right? So V is what you need to calculate. How much will you substitute U as?
Minus 30 centimeters.
Correct. So incident rays are traveling to the right. So anything to the right of the mirror will be considered positive. Anything to the left will be taken negative. And all distances are to be measured from the pole. I'm telling this to all of you. So object distance will be from pole to the object. Okay, you can call it OP, whatever it is, but it's better to call it PO, pole to the object, negative side. So object distance will be minus 30. And Isha, what will you substitute the radius as?
20 centimeters.
Why will you take it positive? Radius also should be substituted following the rules of sign convention. Okay. Radius is the distance from where to where? Pole to center. And it's on the negative side. So radius should be taken minus 20 here. Okay, Isha, is this clear?
Yes, sir.
So 1 by 30 minus 1 by 30 goes to that side, plus 1 by 30 is equal to, okay, not is equal to. There's a minus 2 by 10, that's minus 2 by 20, that's a minus 1 by 10. You can take it as minus 3 by 30. Effectively becomes minus 2 by 30, that is minus 1 by 15. Therefore, V is minus 15 centimeters. And we got a negative answer. That means the image is formed on the negative side at a distance 15 centimeters. 15 centimeters will be somewhere here. I. And in the ray diagram that we drew also, in the original ray diagram, the image was forming in front of the mirror only. Okay. Since we took a problem based on the same case. Okay. So we should get an image of the same nature. It forms in front of the mirror. Okay. Now I told you, always visualize rays. Now one ray is along the principal axis, the orange one, which is already drawn. The reflected ray is also on that line itself. So the image has to lie somewhere on the principal axis. And you visualize another ray, maybe like this, gets reflected this way. Okay. Now you all tell me, what kind of image is this? Real or virtual? Are rays actually passing through that point after reflection or not?
Real.
It's a real image because the reflected rays actually pass through that point. Okay. Now, in case of a mirror, we had discussed this in the last class also. If an image forms in front of the mirror, then it has to be a real image. But if an image forms behind the mirror, rays never go behind the mirror. They get reflected back to the front side. So if an image forms behind the mirror, it has to be a virtual image. Okay, so in this case, it's a real image. Fine. Let's consider a convex mirror. Just a moment. Okay. An object is placed somewhere in front of it. Assume the radius of curvature of the mirror again is 20 centimeters only. Assume object is again placed at 30 centimeters in front of the mirror. Find out where the image is formed. So find out the image distance and also the nature of the image, whether it is real or virtual. Okay. Solve carefully. Make sure you follow the rules of sign convention. 1 by V plus 1 by U is 2 by R. Substitute properly in the formula. And imagine the rays. Okay, at least draw 2 rays. Now one of them will be along the principal axis like this. I'll just draw the incident rays. You draw the reflected rays in your diagram. So one incident ray is this way. You know how it gets reflected also. Consider another incident ray to some other point on the mirror. Maybe like this. Draw the normal, draw the reflected ray, then do the calculation. Okay, some of you have already given the answer, that's fine. But draw the rays. Okay. Again, rays are traveling to the right side. So anything to the right of the pole will be positive. Anything on the left of the pole will be negative. That's the first thing you need to fix. Image distance is what we need to calculate. Let it be as it is. 1 by object is in front of the mirror. Front side. Okay. Pole to object. This is negative. So object distance should be taken as minus 30. Is equal to 2 divided by radius. Radius is from the pole. Okay. We can mark the pole here. To the center of curvature. Clearly, the center of curvature of this surface is on this side. Okay. And this side is the positive side. So radius will be taken plus 20 this time. That's all. Send the 1 by 30 that side. You get 1 by V is equal to 1 by 30 plus 1 by 10. That's like 3 by 30. Effectively becomes 4 by 30. That is 2 by 15. So V is 15 by 2 or 7.5 centimeters. And we get a positive answer. That means image is formed on the positive side. And it makes sense. Let's visualize the ray diagram. You have to draw the normal first. Incident ray is given to you already. Even if not given, you can draw the incident ray, not a big deal. And through the point of incidence, this is the normal. And draw the reflected rays as that angle of incidence is equal to angle of reflection. It will be somewhat like this. Okay. In between these two rays also, there will be infinite other reflected rays. One like this, one like this, and so on. So if you imagine an observer on the left side means in front of the mirror. If you visualize an observer, quite clear, all these reflected rays will appear to be coming from a point behind the mirror. Okay. And that point is this. Okay, so image will be formed behind the mirror. You can check this on your own also. You use a steel spoon, a shiny spoon. You look at the convex side of the spoon, you will see an image and you can feel that the image is formed at a distance greater than the spoon itself. You try focusing on the spoon and you try focusing your eyes on the image. You can feel that image will be formed at a farther distance than the surface of the spoon itself. Okay. Or if you have a convex mirror, you can make use of it. Fine. Now, directly use the mirror formula. 1 by V plus 1 by U is equal to 2 by R. Suppose there's an object very far away from the mirror. Okay, Anugraha, next class we'll discuss some complicated questions based on this. For this class, it will be this only, the basics. We have to discuss what is the focus. Then we can move on to some difficult questions. Yeah, I know these are very basic. Okay, suppose object. You can leave the class if you want. Go and study whatever you want. Next thing we are going to discuss is the focus. Okay. Suppose object is very far from the mirror. Then what will the image distance be? Direct. Very far from the mirror, you assume u tends to infinity. If u tends to infinity, you get 1 by v is equal to 2 by r. That means the image will be formed at r by 2, half of the radius. Okay. This point, which point? The image location when object is at infinity is what we call as focus. And this distance is called as the focal length. Fine. Let me write the definition here. The image location when object is at infinity is called the focus. Whether it's a mirror or a lens. Okay, this is how focus is defined. And the distance of the image, okay, in that case is called the focal length. Okay, so for a mirror, focal length is equal to r by 2. Therefore, we can say f is equal to r by 2. Shashank, okay, you can. Now, if f is r by 2, we can say 1 by f is 2 by r. Therefore, the mirror formula can be expressed like this. 1 by v plus 1 by u is equal to, we derived it as 2 by r. You can now write it as 1 by f. So image distance and object distance can be related through the radius of curvature and also through the focal length. This is what we call as the mirror formula. Fine. Isha, is this clear?